All right, so time to start the second session. Okay, so the first speaker of the session is Professor Jihn E. He'll be talking about unification and invisible action. Please.
Thank you. I thank organizers for the invitation to this, my favorite conference. My title is Unification and Invisible Action, and well, I may introduce some early papers on this, so forgive me that. So this is introduction, invisible action, QCD phase transition, and because I talk on unification, I mention on flipped SU5 from string. Well, I heard Gross-Tor. He has three classes of frameworks. First framework is very big, grand, and it contains quantum mechanics and the symmetries. Within this framework, one can consider theories. His example of theory is quantum field theory, Einstein gravity, and the string. The theory, within some theory, one can build models. Such a model is standard model, axions, and flipped SU5. Well, model should be a working example. Even though the framework may be fantastic, if there is no model example, then some will say that it is a religion. Effort to find a working model is our job toward model theory framework paradigm. So let us work as a particle theorist, building up some model in string compactification. So I wrote a very early papers on invisible action. I claim this is the first BSM model, weak interaction singlet, weak interaction singlet, which contains a very light axion. And I mentioned that it is suppressed by FA, this coupling. And I mentioned another paper, early paper, which you may not know. It was on neutrino magnetic moment. I tried to introduce neutrino magnetic moment to introduce neutrino proton scattering without neutral current. So I tried to obtain very large neutrino magnetic moment, but it was precursor of all neutrino oscillations. As I mentioned, if one assumes a small mass of the neutrino, one can always obtain the magnetic moment proportional to neutrino mass without assumption of two neutrino helices. I mentioned this one. I didn't work on neutrino mass because I knew that neutrino mass times alpha is basically neutrino magnetic moment. Well, in addition, this invisible action can be part of cold dark matter. That is my claim and other people's claim. And string compactification, as we heard this morning, string theory does not allow global symmetries. But compactification leaves some discrete symmetries. If we consider a few lowest terms allowed by discrete symmetry, it may have global symmetry. So this lavender part respect both global symmetry and discrete symmetry. So if you consider this one, you can consider approximate global symmetries. So this was reviewed. Basically, QCD action and all other ALPS, etc. belongs to this framework. where QCD anomaly is the breaking part. It is not written here. It is anomaly. ALPS, which you heard this morning, is not belonging to the anomaly. It must be from the potential. Because if there is anomaly, that is dominated by QCD anomaly. So from string compactification, always, sometimes, some compactification leads to anomalous yuan gauge symmetry. This can be a symmetry for the global symmetry of the invisible axion. So this is known, and recently we wrote this paper. Here, this 't-Hooft mechanism is very important. If a gauge symmetry and a global symmetry are both broken by one complex scalar field, by the Higgs mechanism, then gauge symmetry is broken and global symmetry remains unbroken. That is obvious because gauge boson obtains mass, so gauge symmetry must be broken. But one combination remains out of two continuous transformation directions. One direction remains as a global symmetry. That's an unbroken charge, and this I show this explicitly. You can always combine these two symmetries as one does not depending on any X transformation. This remains as a global symmetry. So if you write down the kinetic energy terms and the mass terms of the action, you can actually move everything to this form, and there is a global symmetry surviving. The model-independent axion is basically the coming from second-rank antisymmetric tensor by duality. This was pointed out by Witten, but this term was written by Green-Schwarz. So I consider this model-independent axion is a Green-Schwarz-Witten axion. So this one, model-independent axion, can couple in the anomalous gauge theory, couple to the anomalous gauge boson. This signals the mass of the gauge boson. And so we can remove this gauge boson coupling to this degree, and there must be one global symmetry surviving below the compactification scale. And here 't-Hooft mechanism works. So this model-independent axion shift direction basically remains as a global symmetry direction. Now, QCD phase transition is important because if QCD axion works as a CDM. So I wrote this one recently. In the QCD phase transition, there is a critical temperature. Above the critical temperature, we can calculate spin degrees of freedom. Below the critical temperature, we can calculate the spin degrees of freedom. And if we consider quarks, if we consider one family of quarks, then above the critical temperature, including gluons, there are 37 degrees interacting very strongly. Below the critical temperature, there are only 3 out of one family. Our UD quarks, there are only pions, pi plus, pi minus, pi zero. Yes. So this number of degrees are very different when universe goes through QCD phase transition. How do we attack this problem? Well, in '84, Daejeon and collaborators considered this model in the MIT Bank model, and Colby Turner in his cosmology book, effectively they considered effective potential with unstable vacuum and true vacuum with parameter epsilon. But we calculate this phase transition effect from the first principles, where I consider this gray part is the quark-gluon phase. In the quark-gluon phase, hadronic bubbles form. The fraction of hadronic bubbles is FH, and the quark-gluon phase 1 minus FH. When universe expand, there can be many bubbles form. Some bubbles overlap with earlier bubbles, and this must be taken into account. I try to solve this problem by introducing phenomenological equation. So the differential equation I consider is the fraction of AH changing on time is alpha times this one. This is the conversion rate of the quark-gluon phase to hadronic phase. This is alpha. This C takes into account the overlapping region. So I consider, depending on C, this is taken to be order 1, and this is the 1. R is the scale factor at the time. So I solve this equation. So this is from basic principles. There are two aspects in this study. First is a strong interaction and action energy density evolution in the evolving universe. So you might know that some people use different expressions for action masses. In the quark-gluon phase, one must use single particle effect. There is no many particle effect present. So U-quark mass, that's a 2.5 MeV U-quark mass should be used, and the lambda QCD. Lambda QCD is basically one particle effect. By interactions of quark-gluons, you measure how strong, how this coupling constant evolve. It is expressed by lambda QCD. So mu and lambda QCD should be used above the QCD phase transition. Below the QCD phase transition, there is no such parameters available. So you use hadronic phase parameters F pi and M pi. Well, you may ask, well, there's a G, ratio of mu over md, but it is just the ratio. It is not directly using the bare value of mu. So you must know what expression you use for this susceptibility in this phase transition. I take into account this effect. I use different expressions for, and recently let people calculate the susceptibility, and they calculate this one. So they express this one as susceptibility. So there is this distinction, and now what I can do now? We know QCD critical phase transition is about 160 MeV. Everybody agrees on this one. 165, 160 MeV. It was calculated in the community. And this is the result of my expression. The point is, this is a complicated picture, but Gross-Pisarki-Yaffe gave a power of the temperature effect of the instanton effect, strong interaction by instanton effect. That was given by power, minus 8.16. That was the power. But they didn't give the overall coefficient. What is the overall coefficient? We should know the overall coefficient. At the critical temperature, if the universe goes to critical temperature, then at that point, 100% are the quark-gluon phase. There I know what is the spin degrees of freedom in terms of quark and gluon. 100% quark-gluons. Above the critical temperature, because I know the number there, I use the power, instanton power to go to higher temperature. So I use this one, because I know the overall coefficient, use the instanton power. Then I calculate T1, where axion field start to oscillate, equating MA equal to 3 times the Hubble parameter. So if I use a different axion mass, basically T1 can be different. Then if I calculate T1, I evolve from there, because I know now overall coefficient because of this information. I use this exact expression for the axion density and evolve according to evolving universe of the axion field. So that's the figure I have. So that I calculate, and then I calculate evolution. So basically, in this we notice there are 3 different free energies. Internal energy is used for the first law of thermodynamics, and this Helmholtz free energy is used in the evolving universe. And this Gibbs free energy. Gibbs free energy is useful for the phase transition in my calculation, because Gibbs free energy the parameters are temperature and pressure. In the phase transition, first order phase transition or crossover, this bubble are formed at the same temperature and the same pressure. So it is formed at rest, same pressure. So I use Gibbs free energy, and as time goes on, somehow this expand and used now this evolving universe. I use this expression. So now I have to know this. There is a pressure expression and temperature. So I have to know the pressure in the quark-gluon phase and the hadronic phase. In the hadronic phase, pressure is basically long distance effect with many particles. Long distance effect is wavelength is over critical temperature dimension. So it is overlapping. So this was attacked by Huang's book in statistical mechanics. There's some equation. This one, I use this equation in relativist form to calculate the pressure in hadronic phase. I know the hadronic phase pressure now. So I equate the Gibbs free energy at the quark-gluon phase and hadronic phase. When quark-gluon phase dVq is becoming to hadronic phase, I have this expression. Now I know I obtain this equation, and I calculate conversion rate alpha in my previous differential equation. So I have every information, and this alpha is calculated. This is of 10 order 10 to the 4 MeV. And as I said, depending on the axion mass, depending on different axion mass, this is 3 times Hubble parameter. Different T1s are used for different axion masses. If one axion mass is given, this when initial misalignment angle is not is large, there is a bottleneck period, as it is shows. So in every calculation, I use the first peak. First peak is the beginning of harmonic oscillation. As you notice from every figure, after first peak, it behaves like a harmonic oscillation. So in this calculation, this bottleneck period is a bottleneck period exaggerated here. So for every axion mass, I calculate this one. From here, I use a harmonic evolution. So in this way, I'll calculate this one. And this is, so this is from T1, I calculate until first oscillation. So it doesn't decrease very much. This one, zeta bar doesn't decrease very much for every case. From first oscillation to end of the QCD phase transition. End of the QCD phase transition, I calculated, I didn't explain in the figure, but I will show anyway in later that end of the QCD, when FH becomes 1, is the end of the QCD phase transition. Until then, this decreases depending on different axion masses, has different decreasing power. So this part explains the QCD phase transition. How zeta bar evolves from the first oscillation until the end of the QCD phase transition. From end of the QCD phase transition until now, I can calculate this way because I use this evolution equation, zeta bar evolution equation. And this has a kind of parameter symmetry. If I change M0 some power and change zeta bar to compensating power, this is invariant. So this many oscillations, because from about 10 to the minus the 4 second until now, roughly until now, 10 to the 17 seconds, there are so many oscillations of the axion field. I cannot do that. So I use this parameter symmetry and split this whole region by many steps. And in fact, for one step, I compare this shift 100. This is roughly 100 shift. I compare the original equation in this region, for example, this one, and this parameter shift shows this one. It is exactly overlapping. So I can do this calculation, and I multiply this factor, this factor, this factor. So that's the result of this is actually exaggerated. So end of the QCD phase transition until now, it is 3 times 10 to the minus 17. I calculate this ratio in this way. And from until end of the QCD phase transition, I obtained just before with some parameters, different axion masses. I parameterize in this way. So multiplying everything from theta 1, now this is 10 to the minus 17. It is expressed in this way. Actually, RF1 is given here. This is 10 to the minus 18 zeta 1 bar. So that is most recent calculation, taking into account the QCD phase transition from the first principle. And I talk on unification. I like flipped SU5 from string. Well, SU10 splits to SU5 times U1x in the flipped SU5 language. And the George-Glashow SU5 is x equal to 0, basically, in this notation. And in this, 10 bar contains positron, and 5 contains anti-d quark. Flipped SU5 contains, 10 bar contains d quark instead of u, and 5 contains anti-u quark. So there's a difference. So Higgs are represented in this notation 5, 5 star, and 5 minus 2, 5 star plus in this notation. So the flipped SU5 arrives from compactification of a heterotic string very easily. And you cannot obtain George-Glashow SU5 from compactification because you do not obtain adjoint representation from heterotic string if you keep only up to level 1, the unification condition. So adjoint representation you cannot obtain. As it applies to SO10, E6 also. So I like this flipped SU5. Well, George-Kuhn-Weinberg expression in the unification of these gauge groups leads to sine square theta W of this form. This is 3/8. But axion coupling is basically, it is unified, it is inverse of this one. This is the inverse of this one, actually. If unification is applied. And this unification point, this one is grand unification point, and this one basically stays all the same. And string compactification, the easiest way is to split internal 6 dimensions to 3 2 tori. G12 has one tori has one fixed point. Second torus has 3 fixed points, third torus has 1 fixed point. So in total, you multiply this, there are 3 fixed points. So this is the simplest case. In orbifold compactification, G12 is the simplest. So flipped SU5 can be obtained. There can be SU5 times SU5 prime, SU2 prime. Well, Lawrence talked about modeling well. By appropriate compactification, you can obtain this one, but it is not exactly symmetric. This contains only 1, 10, plus 5 bar, 1, 5 bar. So it is not exactly symmetric, but anyway, you can cook out some kind of models. So the U1s, there are many U1s are appearing, and there are some anomalous U1s. This anomalous U1 is the basis for the axion I mentioned in the beginning. And I obtained these 3 families, basically. One family appears from U, untwist sector, this untwist sector. 2 families arise from twist sector. And this one is T6L, some kind of sector. And I obtained some kind of R parity, G4R. Well, I show this G4R. There are many other singlets. This one is 10 plus 10 bar, 10 plus 10 bar, breaking flipped SU5 to the standard model. And there are G4R quantum numbers are here. So G4R can be, actually this is U1R. This is U1R. It is U1R because I calculate this U1R because I talked about 3 internal space. One internal space has one phase. So I introduce one phase in one internal space. I combined U1s from E8 cross E8 prime with U1s from internal space, 6 internal spaces. So I obtained all quantum number in this way. Yes, I show some examples. If this 4 quantum number develops vacuum, this is needed to develop vacuum expectation value to break flipped SU5 to the standard model. This breaks to G4, discrete symmetry G4R. It is basically G4R. It is, in a sense, contains space-time G4R because I introduced internal space quantum numbers also, not only U1s from E8 cross E8 prime. And there are many things. There are some phases I wrote, so this is useful to construct effective terms. I can obtain all terms. With this, I obtain all flavor matrices. From top quark mass is heavy, mu term is absent, except one proton decay problem. But anyway, this one is very interesting, string compactification. There are many singlets which can be used to obtain mass matrix texture. Actually, this leads to fermion mass texture, exactly. So, in conclusion, I showed unification from string and axion energy density is expressed in this way. Actually, it is in this form. I showed this one. And TF is the QCD phase tangent starts from critical temperature. It becomes 1 exactly. I calculate this one. It was about 6 times 10 to the minus 5 second. In my calculation, QCD phase transition ends at universe temperature 10 to the minus 5 second, 10 to the minus 5 second, and the scale factor increased from here to here is about 2.3. This is about 2.3. So I use this one. I use this one to calculate the ratio of zeta bars from TF to T now. So I use this one. So if current axion energy density is 10% of all CDM, we need zeta bar now over zeta bar F 10 to the minus 20. I showed that it was about 10 to the minus 18. So a kind of fine-tuning of 100 is needed, basically, because they're too much. It is too much. So zeta bar initially, zeta 1 was initially about 0.01, can lead to 10% axion mass now. So thank you.
Okay, thank you very much for perfect timing. Questions? We can have many questions and comments. No questions? No comments? Okay, so let's take a speak again.
Okay.
Okay, so our second speaker is David Marsh from Daejeon. He'll talk about axion searches.
Thank you. Okay, yes, so thanks for the organizers for inviting me here. It's very nice to be in Korea for the first time. I'm going to be talking about searching for axions. So let's begin. What's the axion parameter space? So the things that one is interested in are, of course, masses, the energy density in the universe, the couplings of a particle to the standard model, and in the context of the string landscape, how many of these axions are there. But these are not isolated parameters. Each of these parameters, we have to build some assumptions into it. these are those assumptions. So the mass, of course, arises from an overall potential, and this will contain interparticle interactions, the axion 2-to-2 scattering rate, things like that. Then the energy density, whenever you calculate the axion energy density, your interpretation of that depends on the cosmology. So as we were just hearing, it can depend on details of the QCD phase transition. It could depend on dilutions, as was talked about by Lawrence this morning, and all kinds of assumptions about cosmology. The standard model coupling is, of course, broken up into couplings to all the different parts of the standard model, the photon coupling, the nucleon coupling, etc. And anything we learn about the number of axions is weighted by our prior on the landscape, our prior on where should axions be coming from, with different masses and potentials and the like. But we're at a cosmology conference, so one of the most interesting things is that all of these different parameters feed in via cosmology to give us the energy density in axions today, which is the thing that we might want to try and detect. And this gives us axions that can be all kinds of different contributions to the energy density of the universe: hot dark matter, cold dark matter, fuzzy dark matter, dark radiation, dark energy, inflation. I'm going to be focusing on axions as cold dark matter or fuzzy dark matter, and I'll define what that means. So you're probably familiar with this picture. Axions are a cleaning product, but there's a whole array of different products on the axion market. And you can do all kinds of things with cosmology: dark matter, dark energy, inflaton, axions, and their role in CP violation might even help with baryogenesis. So let's talk about, I'm going to talk about 3 different ways to probe axions, and each one is going to give us a handle on a different subset of those parameters, so that overall we'll have looked at all of them. I'm going to start with black hole superradiance, and how black hole superradiance can be used to constrain the axion mass, certain aspects of its potential. And it's going to be the only thing that I tell you about that can really be used to constrain the number of axions. And to get more details about all of this, I'm going to be talking about work with my collaborator Matt Stott, and he'll be giving a talk tomorrow. So, black hole superradiance, how does it work? So, you have an axion orbital set up around an astrophysical rotating black hole. And that orbital is superradiantly populated from vacuum fluctuations. So you don't need any axions around as dark matter. So this is a very nice property because it only really depends on gravitational physics. You just need a massive field. So what happens? This is the effective potential of a scalar field around the rotating astrophysical black hole. There's the angular momentum barrier here, and then there's the potential well created by the particle's mass and its gravitational attraction to the black hole, and it can be confined here. Superradiance depends on this coupling parameter, alpha, which is just the usual Newtonian coupling, and what happens is that the particle gets confined here, and then and then it can extract spin off of the black hole, just like if you throw a ball at a rotating cylinder, it can bounce off with more energy than it came in with. And it's just like any other superradiant process in physics, like say Cherenkov radiation. And then so the particles that sit here extract spin from the black hole and extract mass from it, and there's a time rate of change of those goes like a superradiance rate, which is proportional to some power of this interaction constant, and is maximized when this constant is of order 1. So what that tells you is that it's maximized when the axion Compton wavelength is of order the gravitational radius of the black hole. What this means is that axions of a certain mass extract spin from black holes. And because we observe astrophysical rotating black holes, that means that certain axions cannot exist, or in fact this applies to all kinds of bosons, it applies to vectors and massive spin 2 particles as well. So because we observe rotating black holes, it tells us that axions with a Compton wavelength comparable to those black holes cannot exist, or else they would have extracted the spin via this process. This is a summary plot. It's quite busy, but it tells you all that you need to know about constraints on axions from superradiance. So I've got two x-axes and 2 y-axes. The x-axis at the top is the axion mass, and that refers to these black curves here, and the y-axis here, the exclusion probability. So the exclusion probabilities are large for a range of masses. On the y-axis here and the x-axis here, I'm plotting the black hole mass as a function of its dimensionless spin, and the observations are labeled here. These are stellar black holes and these are supermassive black holes. And then along the same black hole mass axis, these are the superradiance rates. Oh, sorry, these are the contours due to superradiance where black holes should not live. So because these are spun down on a timescale faster than their astrophysical timescale, no black holes should live in these contours, color-coded by the axion mass. So you can kind of overlap the colored contours with the data by eye, and see how these exclusion probabilities arise. And these are completely model independent. It doesn't depend on it only depends on the axion mass. It doesn't depend on the energy density or depend on any of its couplings to the standard model. All you need is a massive particle around. And so the stellar black holes exclude a range of axion masses from about 10 to the minus 11 to 10 to the minus 13. And the supermassive black holes with larger uncertainties exclude a range from about 10 to the minus 16 to about 10 to the minus 20. And we'll come back to this number later. And there's this interesting gap in the middle around 10 to the minus 15 EV, which is about the mass that you need, which is about the mass that you get, interestingly, from the gut scale coupling and string compactifications. So there is one assumption that comes into this, which is the axion self-interactions. So the potential, the axion 2-to-2 scattering can shut off this superradiant process. If the 2-to-2 scattering, two axions in the cloud annihilate into two axions, one that remains and one that escapes, this process can shut off the superradiance. And so Arvanitaki and collaborators computed for this potential, the upper limits on the axion decay constant for which superradiance still holds. And so you see that for the stellar black holes, the superradiance limits only apply to decay constants above 10 to the 14 GeV. And for the supermassive black holes, the limits only apply for decay constants above the gut scale. You can also use, and I think this is the coolest thing actually that you can do with superradiance, you can use it to constrain the number of possible axions. So if we take the probability distributions that we get, say, from random matrix theory for axion mass distributions in the string landscape seriously, then we should also take the tails of those distributions seriously. So you can ask, how many axions do I have to have until I have a significant probability to populate a tail and land just one field landing in that superradiant region excludes the whole distribution? How many fields do I need for that to become probable? This is expressed again in this plot, which Matt will talk about tomorrow. So here we've taken a distribution with a log normal distribution for masses, parameterized by some spread sigma for different axion masses, and asked how many axions do you need before that's excluded. And you see that quite generally, theories with large numbers of axions are excluded. And it's an interesting number. It's in the range of 30 to 100 fields. Anything with a large number of axions is in some sense in conflict with the superradiance data. So that's why I think superradiance is really interesting. It gives us a really neat probe of the masses, potentials, and number of axions independent of cosmological assumptions and independent of assumptions about couplings to the standard model. And it's the only case that I know of where you can constrain the number of fields. Now we're going to move on to ultralight axions. Why are these interesting? These are interesting because we can use cosmology to constrain the energy density. So I'm going to be placing constraints on the mass, in some sense the potential, and the energy density. We can only constrain the energy density with cosmology. Only cosmology gives us access to the energy densities and components. So this gives us the range of masses we have to look for, a range of masses that have effects on cosmology. So in this context, I'm talking about axion dark matter. It's a non-thermal classical field governed by the Klein-Gordon equation. It has two distinctions from cold dark matter: the role of Hubble friction, the time when the field goes from behaving as a cosmological constant to pressureless matter, as was talked about in the last talk. And then in the perturbations, there is also a distinction between axions and cold dark matter in the gradient pressure. And what can we do with cosmology? So with a cosmological survey, like the CMB, or like a galaxy survey, we need to find a scale where these two bits of physics matter. So the scale where this happens is the time when the axion mass becomes comparable to the Hubble constant. This sets a time scale, a redshift. It also sets a length scale, a wave number, the wave number of perturbations that were roughly the size of the horizon when this happened. So this gives us an access to a range of m, sorry, not m, not 1 over m, set by the k-min and k-max of our survey. That tells us what range of axion masses can we hope to use cosmology to constrain to place constraints on the energy density. And we can do this using the CMB. This is showing for axions that begin to oscillate in the radiation-dominated era. They look like dark matter, but if this oscillation happens close enough to the transition from matter to radiation domination, you have an effect, a significant effect on the expansion rate during the radiation-dominated era, which means you will change the silk damping scale in the CMB, and you change the heights of the acoustic peaks. So here I've got all the dark matter being in very light axions, and I'm changing the mass. I'm increasing the mass from 10 to the minus 27 eV, the Hubble scale at matter radiation equality, and I'm increasing it, and each time I increase the mass, the amount of silk damping goes back towards CDM. So by measuring the heights of the acoustic peaks, we can constrain the mass and energy density of axions with masses of something just slightly larger than 10 to the minus 27 electron volts. We can also constrain lighter axions than this. If axions begin oscillating in the matter-dominated era, they behave in some way like dark energy. There's a period of time where the field is frozen, contributing like a cosmological constant, and this changes the expansion rate and the distance to the surface of last scattering. And that's what I'm demonstrating here. So here, what's happening is I've got some fraction of the dark energy density in an axion with a mass in the range 10 to the minus 30 to 10 to the minus 33 electron volts. When the axion's heavy now, I have less dark energy, so the acoustic peak is at larger angular scales, and then that transition from W equals minus 1 to W equals 0 distorts the integrated Sachs-Wolf effect. And now, as you decrease the mass, as you go closer and closer to mass to 0, closer and closer to the Hubble scale today, effectively, such an axion becomes indistinguishable from the cosmological constant. So this gives us a bracket of masses that we're sensitive to, somewhere around the Hubble scale today, and somewhere around 10 to the minus 24 electron volts, where the effect on the acoustic peaks vanish. You can see this here. Here are some samples from MCMC chains at different axion masses. In this case, colored by omega CH squared, you see that an axion can replace cold dark matter for masses above 10 to the minus 25, 10 to the minus 24 eV. And then in here, I've colored my MCMC samples by omega lambda, and you see that once you get below 10 to the minus 33 electron volts, omega lambda can go to 0, and your axion can replace omega lambda. Putting this all together, you see the following take on axion energy density constraints. So I'm constraining now the energy density in light particles as a function of their mass using the CMB. And the constraints are roughly 2.5%. So these light fields have to be less than a few percent of the total dark matter content. This is interesting because it's a precision test of cold dark matter. It's a precision test of cold dark matter over a large range of scales, all the range of scales probed by the CMB, all the linear scales in cosmology. Remember, it was that K-min, K-max of my survey that set this. Black hole superradiance constraints started to kick in 4 orders of magnitude from here at 10 to the minus 20. How can we close that gap? We need to go to nonlinear scales. I'll skip that. we need to go to nonlinear scales. Galaxy formation. So this, because my axions have, they do not behave like dark matter on scales smaller than the horizon when the field begins to oscillate. This gives rise to a Jihn scale and suppresses high Z galaxy formation and high K matter power spectrum. This is the galaxy UV luminosity function. Matching this to Hubble data tells you that axions cannot be all of the dark matter unless they are heavier than about 10 to the minus 22 electron volts. If you do this for the Lyman alpha forest, you find a bound about an order of magnitude better. The Lyman alpha, this is now the fraction of dark matter in axions as a function of the mass, using Lyman alpha forest data. Of course, these two bits of data have very different astrophysical assumptions built into them. And the Lyman alpha forest tells you that roughly your axion has to be heavier than 10 to the minus 21 eV. We still haven't closed that gap to black hole superradiance. We have to go to even more nonlinear scales and inside galaxies. This is where the so-called fuzzy dark matter model and phenomenology comes in. So, as pointed out by Lam Hui et al., the axion de Broglie wavelength modulates the energy density in inside galactic halos on kiloparsec scales. As observed in simulations by Shive et al., this also gives rise to cores in the centers of density profiles. Both of these phenomena can be understood as a kind of a two-body relaxation between quasi-particles with the following relaxation time. It's of order the age of the universe in typical galaxies for axion masses of 10 to the minus 22 eV. As the mass gets larger, the relaxation time gets larger. So you don't want this time to get smaller than the age of the universe in any system, or your system would not be stable. It would be relaxing. But really resolving this in detail requires beyond n-body simulations. So we're looking inside galaxies. You have to do simulations not of an n-body, but of this. This is the Schrödinger-Poisson equation, and it's fundamentally different from cold dark matter, warm dark matter, or self-interacting dark matter. But fortunately, these simulations can be done. They're being done by some of my colleagues in Göttingen. This is a beautiful snapshot from a simulation by Jan Veltmat, a PhD student, using a hybrid n-body and Schrödinger method to make zoom-ins. So you see that the large-scale structure of the cosmic web looks very much like in cold dark matter. But zooming in on the finest grid levels and solving the Schrödinger equation, the insides of galactic halos have this fluctuating quasi-particle-like structure and dense cores. And there's a particular time scale, this is the power spectrum in time of this core. There are particular time scales of fluctuations. Fluctuations like that, as I said, disrupt stellar structure. They have a relaxation time. And we can use this to start to put more constraints on fuzzy dark matter and try and close this gap, maybe, to black hole superradiance. So this is some preliminary work that I'm working on with Jens Niemeyer, where we've looked at the survival of the star cluster in Eridanus 2, which is an ultra-faint dwarf, in the presence of these fluctuations that we observe in simulations. And we think that we can increase the constraints on, so this is again the fuzzy dark matter mass, as a function of the fraction of dark matter. And we're starting to push constraints on this model into the few times 10 to the minus 20 limit. So it's and black hole superradiance would rule out the model over here. So we're really hoping we can close the gap on this model. And then from the CMB to black hole superradiance, we'd have constraints on axions over 23 orders of magnitude in mass. Of course, relating to different assumptions on the energy density, potential, number of fields, etc. The final thing I want to tell you about in the last 5 minutes is the constraints on what's most interesting to many people, the axion couplings to the standard model. How do we search for axions on Earth? So here, the main parameters we're interested in out of that axion parameter space from the beginning are the mass and the couplings to the standard model. I'm actually going to give a biased view of this. I'm going to be talking about experiments going on mostly in my new home in Germany. Of course, there's a lot of exciting stuff happening right here in Daejeon at CAP, and I urge you to look into that. So let's start with the classics. There are 3 classic ways to detect axions. They all work by the axion coupling to electromagnetism by the Primakov or inverse Primakov process. This coupling between axions and E dot B. Those 3 classic ways to look for axions are light shining through a wall, helioscopes, and RF cavity haloscopes. There are existing constraints from light shining through a wall experiments, ALPS and OSCA, but there's a very powerful new upgrade to these types of experiments, ALPS 2, that is in commission and taking data, I believe, at Daisy in Germany. For helioscopes, which is axions come from the sun, hit by a magnet, turn into photons. The existing limits come from CAST, the CERN Axion Solar Telescope, but they'll be improved by a few orders of magnitude by EAXO, which is now in quite far stages planning to being built at Daisy. So again, Germany leading the way in this. And then RF cavity haloscopes. The existing experiment is, of course, ADMX, but there's a whole generation of new high-frequency RF haloscopes under development, ADMX2, Kultask, and many more. And they give you this picture of axion parameter space. This is the axion photon coupling, the axion mass, QCD prediction, exclusions from CAST and ADMX, and projected exclusions for EAXO and ALPS2. But what's really exciting is the new developments in axion haloscope, in the axion haloscope community, the haloscope new wave. So I'm going to tell you about 3, in 2.5 minutes, 3 new haloscope ideas, all 3 of them going on in Germany. So there's MADMAX. MADMAX, it uses electromagnetic radiation emitted from dielectric surfaces in the presence of an axion. When you layer up many of these dielectrics, you can get coherent addition of these photons, and it worked in a way like a resonant cavity via coherent addition. This experiment is under construction and is funded and is being constructed at Daisy. It already has a prototype to test the idea. These are those dielectric disks of sapphire. This is what the full experiment will look like. I think there will be 10 of these, and they'll be in an old Hera yoke, so this gives you an idea of the size of the thing. But it's very much going to happen. And MADMAX will do a lot to axion constraints at high frequency. So this is the ADMX constraints at a few micro EV. MADMAX will fill the gap all the way up to a few hundred micro EV, and at higher frequencies than the other RF haloscopes, such as Kultask or ADMX-HF. The second idea is the NMR haloscope. This is Casper. There are 2 versions of Casper. So what Casper does is it uses resonance now between the axion mass and the nuclear llama frequency. So the nucleons process in an external magnetic field, nuclear magnetic resonance. If you tune this to the axion frequency, you will resonantly excite the magnetization. You can do this in 2 ways. You can couple to the neutron electric dipole moment itself, in which case you need an electric field, and then you measure the magnetization. Or you can just use the axion-nucleon coupling, and then you spin polarize with the magnetic field, and your additional term that creates a pseudo-B field is the dark matter velocity. This idea is called Casper Wind, and this is under construction in Dimitri Budke's lab in Germany, in Mainz. These are the projected exclusions for these in the dipole moment coupling. Casper Electric could, in its final stages, make some inway into the QCD axion at very low mass. And for the nucleon coupling, won't get to the QCD line, Casper Wind, but will make some significant increases over the astrophysical limits. In the last 30 seconds, I want to tell you about my own contribution to this, an experiment that I called 2RAD for topological resonant axion detection with a lot of collaborators in Germany. We use the idea of antiferromagnetic resonance, which gives rise to pseudoscalar spin waves with again a magnetic field tunable mass, like the Lama frequency of the nucleons, but now in the antiferromagnetic frequency range of milli-eV terahertz. And by using this with particular Dirac materials, this is bismuth selenide, that have a chiral anomaly, we think we can make some kind of detection to axions at high frequency in the terahertz. So that's all I wanted to say. Thank you very much.
Thank you for a nice talk. Questions?
Yeah, hey. Yeah, thanks, very nice talk. Do you mind going back to the black hole superradiance, the spin exclusion plot?
Yeah. All the way back.
Yeah, the next one, yeah, this one. So I was wondering why you get an exclusion at 10 to the minus 11 EV, because there don't seem to be any data points there.
So that's because these two axes are different. What you should look at is the color code here. So this is orange, this is the roughly orange one, and the roughly orange ones overlap with these data points. We've kind of tried to align the axes to help you guide the eye, but they're not really exactly the same axis.
I see. And then maybe a quick second question. So when you were saying there's a limit of about 30 on the total number of axions, that must depend on some kind of prior assumption of what mass range of axions you're spanning.
Right. So we've color-coded the lines here with the central value of a log normal distribution.
I see.
So it's for all log normal distributions centered between 10 to the minus 22 and 10 to the minus 10 EV, with spreads, log spreads in the range of 0.1 to 100. So it depends on the shape of the distribution, and it's the number of axions in that distribution. So of course you could have a second lobe at very high mass.
Sure. Thanks.
Any other questions? Okay.
Hey, thanks for a nice talk. You mentioned the hybrid n-body code used to solve the equations. How more difficult is it to implement than a normal dark matter only simulation?
So, so first of all, the reason you can't do this on all scales is because you want to resolve at high density. But to accurately solve the Schrödinger equation, you need to resolve density and phase has large gradients and voids. So if you wanted to do this everywhere, you'd have to refine grid everywhere. How much more difficult is this to do than an ordinary n-body simulation? Well, it's about a PhD's more difficult. It's what Jan's been doing for his whole PhD. You have to take, so they take a standard code, I think they take ENSO, and you have to construct boundary conditions on your smallest grid level that give you the right matching to these variables between these variables. So that's relatively tricky. And then you have to get your own PDE solver on the finest level. But it's not like super hard.
Okay.
But they still can't run massive boxes, so this is about the biggest box that was able to be run.
Thanks.
So, okay, perhaps one last question. So I don't see any hands. Okay, so let's thank the speaker again. Thank you. So is we back? Okay, so let's convene at 2 p.m.